Hello and welcome to the second lecture on periodic classification and periodic properties for class 11 and the integrated IIT JEE and NEET examination and all other competitive tests. We had discussed the 118 elements, their positions in groups, in periods, in the periodic table, in the long form of the periodic table, and we also knew how to generate the atomic numbers by following the magic numbers. For the S block, P block, and D block automatically can be found series wise. And then the connecting lanthanide connecting the vacant space we have kept at 57 that starts the lanthanide from lanthanum, ends at lutetium. 71 then comes back to the same 5D series at hafnium 72. And then goes up to 80. Again, there is a connectivity in the actinide series. Actinium is 89, then there is a vacant space, and all the actinide elements from actinium to lawrencium have been kept at the bottom. And then again, after 89 to 103, 89 is actinium, 103 is lawrencium, and then 104 is rutherfordium. So my question now will be to don't look at the periodic table that you have just now drawn. Tell me, Swam, what is the element present in the sixth period belonging to the 16th group 16, and what is its atomic number? You have to be thorough. Sixth period starts with cesium, and we come up to 16th period, just one column before halogens. What is that? Yes.
Sir, polonium.
Precisely, polonium. What is the specialty about polonium?
Sir, polonium is the first radioactive element.
Yes. Although theoretically, or yeah, almost virtually, bismuth is a stable element, but nowadays it has been discovered that bismuth too is a radioactive element, but its half-life period is more than the age of the earth. That is why for all practical purposes we consider bismuth stable. Now a question comes to what is its atomic number? Now Swam again.
Sir, 84.
And these are variable because these are the isotopic mass or the mass number of that particular isotope. If it contains multiple isotopes, then you have to write the mass number, which is the rounded off whole number to the isotopic mass at the top. I'm not asking about that. Then next question to Mr. B. This is S. Mr. B, can you give the period and group number for the element osmium?
Sir, sixth period, and eighth group.
Because iron, ruthenium, osmium. They belong to group 8. And below osmium, you can just look for fun. This is highly unstable synthetic element. Can you just name what is the element below osmium? Just look to the periodic table if you don't remember. Yes, Bisma? Hari? अरे देखो देखिकिरी कुह
Sir,
हम्म ଦେଖୁନ osmium ପରେ କଣ?
sir,
ହାସ୍ୟମ୍.
Siam.
ହାସ୍ୟମ୍. Actinium, Rutherfordium, Dubnium, Seaborgium. Actinium, Rutherfordium, Dubnium, Seaborgium, Borium, Hessium, Meitnerium, Darmstadtium, Roentgenium, Copernicium, Neonium, Flerovium, Moscovium, Livermorium, Tennessine, Organization, 118. So, this is Hessium, but we will not talk about Hessium anymore. Okay, then what is its atomic number?
Sir, Smium was 76.
How did you know?
Sir, magic number.
Now, iron is 26,
26.
then add 18,
Three.
this is 44, is ruthenium. Because in the group, in the period 6 after hafnium or after say lanthanum, you have crossed the 4F series, therefore you have to add 30, you know, 2. You have to add 32. You have already covered that period. I mean, that number of elements through the lanthanides. So it becomes 76. Got it? So you can also use the magic numbers the first one of the 3D series, whatever the atomic number, then plus 18 plus 32. Plus 32 will give you the remaining elements in a particular group, transition group. Understood?
Yes, sir.
And now question 2, Mr. Soyam. Write the electronic configuration of platinum from the PT, starting from the noble gas configuration, the noble gas which precedes platinum, uh, put it in the square bracket and just forget about its electronic configuration up to that. Then you start looking to the periodic table. Look to the periodic table and tell me the electronic configuration of platinum. Yes, Mr. S. Getting late.
Again, sir, Hela.
Uh,
Sir,
cool.
Sir, Genon 4F14, 5D9, 6S1.
Yes. So this will be, you just remember that in the third transition series or the 5D series, there is only one anomaly, two anomalies, including gold, platinum and gold. So platinum comes. So it should be, since it is palladium, nickel, palladium, platinum, it should D8. Should be 5D8. Of course, 4F14 is already gone since you have crossed hafnium, jumped from lanthanum to hafnium. So that will be there. And since it will be one electron exchange, it will be 6s1, 5d9 precisely. Yeah, କହିଲ ତ?
Again, sir.
And how many unpaired electrons are there in the ground state? So there is one unpaired electron here, one unpaired electron here. So there are two unpaired electrons of platinum in the ground state. So you can find out its spin magnetic dipole moment from the formula n into n plus 2 square root Bohr magneton. Got it?
Okay, sir.
Now the last question to be is give the electronic configuration of say bismuth. This is 83 on the basis of periodic table without looking to the Madelung's order. Because when you go in a period, first it's S, the same periods S, then n minus 1, the previous cells D, and then same cell. Of course, in the 6th and 7th period, you cross 4F and 5F. If you cross lanthanum, jump to hafnium, or you jump actinium to the rutherfordium, you cross rutherfordium to copernicium. All these things, nobody will ask you about its electronic configuration. Just it is theoretically predicted without any anomaly. They have written, if you Google search, you will find without any anomaly. 5F14 is complete. Then rutherfordium is 62. 61 is actinium, and then rutherfordium is 62. 63 actinium, rutherfordium, dubnium, dubnium, and so on. So tell me.
Sir, Gen1 4 14 5D 10 6S2 6P3.
Yes, 6S2, 4F14 is complete, 5D10 is complete, and then since it belongs to the group 15, nitrogen is a P3 configuration, NS2 and P3, all nitrogen, phosphorus, arsenic, antimony, bismuth, they all belong to the NS2 and P3 group 5A or newly named group 15. So it will be 6P3. So now the valence shell is 6. You can, just like nitrogen, the same, there will be 3 unpaired electrons and a lone pair. Now my last question to S, I forgot to tell you to remember the elements according to groups. Sequentially, you just remember. ଆମେ generate କରିବା ପାଇଁ period wise କରିଥିଲେ, କିନ୍ତୁ group wise ତମେ ମଧ୍ୟ ମନେ ରଖିବ. For example, oxygen family, I ask Mr. S all the elements in sequence in oxygen family, starting from oxygen, without looking to periodic table. Try to recollect.
Sir, oxygen, sulfur, selenium, tellurium, polonium,
And just try to look.
livermorium. Sir, livermorium.
Yes, livermorium. Nobody will expect that element that you remember, but if you just remember, it's definitely one way you have an edge over others. Good. So can you name Mr. Tripathi the group 13 elements, group 3A, what we call the boron family?
Sir, boron, aluminum, gallium, indium, thallium,
Neonium? Ne?
yes, and new.
Neonium? Ne? Neonium, that's all neonium, nahi? NH.
Yes, sir.
Copernicium salapre, neonium, flerovium, moscovium, livermorium, tennessine organism. So, okay, good. So, seguଡାକ ଯଦି ମନେ ରଖିନଥିବ ତାକୁ ଆଉ ଥରେ ଟିକେ କରିଦିଅ. I want another question. Supposing I need the cobalt group, the cobalt group, because transition elements have similarities across series, also along groups, which is not found in normal representative elements S block and P block. They do not have similarities across period. They have similarities along groups, but transition elements, the D block and F block, these two, transition in inner transition. Lanthanides and actinides, they are combinedly called inner transition. They have similarities along series and also along groups. Yes, cobalt group.
Sir, cobalt group टा कहबी.
Ah,
Okay, sir. Sir, cobalt, rhodium, sir, iridium, sir, meitnerium.
meitnerium. Okay. Well, let me check. Say meitnerium টা পুরো আমি চেক করে দেবো. Yes. And can you tell me, in general, Mr. S, the configuration of these elements starting from cobalt? You have to say cobalt 4s something, 3D something. Just forget about its previous noble gas. Just tell me the valence shell or and the N-1D also to be included because it is a transition element. You have to include the N-1D because it is practically included in the valence shell. It's the N-1D electrons take part in the bonding. Yes, cobalt kehte. What is the atomic number? 27. 27 means 3d7.
Sir,
28,
कहबी.
88. Yes,
Sir, argon, 3d7, 4s2.
precisely. Then you have to remember, you go down, you have to remember, in a 4D series, there are a lot of anomalies starting from, starting from yttrium, zirconium, niobium. Starting from niobium, you find anomaly starts. So you have to remember, yes, rhodium anomaly thila ki. Accordingly, you just switch electron. Tell me, rhodium. Once you thorough becomes thorough in periodic classification and periodic properties that we are going to take up today, then you are quite strong in inorganic. And of course, writing building equations, the basic concept of building equations, different types of reactions, though you will be encountering with multitude reaction equations which you never knew, but you can rationalize the logic why this has happened. If something is missing out, if some species has been oxidized, the oxidation number has risen, increased. But where is the other reduction where the oxidation number is decreased? If you are finding something missing out, the logic is missing, then this is wrong. It's not possible. It's not possible that some element will increase its oxidation number and no other element will decrease its oxidation number, including the same element if it is a disproportionation reaction. Yeah,
Sir, rhodium रा হচ্ছে sir krypton, 4d8, 5s1.
yeah. 7 হবা কথা because D7 তার তার পূর্বটা কোবাল্ট D7 মানে D7 হবা কথা কিন্তু অ্যানোমালি ଅଛି মানে গোটে ইলেকট্রন চালি আসিব 5s1 4d7 and then कोबाल्ट रोडियम इरिडियम इरिडियम में कोई एनोमैली नहीं है तो क्या होगा
Sir, iridium रा হবো sir xenon, 4f14, Sir, 5d7, 6s2.
Yes, there will be no anomaly. 6s2 आगे लिख दो 6s2 5d7 4f14 देखिदो बारी है ये तो हाफनियम परे अछि तो डेफिनेटली 4f14 आसीगलानी precisely. Now my last question is to Mr. T, Mr. Tripathi. Oh, what are the nickel group elements, stable elements? I am not interested in rhodium.
Sir,
And then uh,
nickel, palladium,
platinum.
platinum.
Then electronic configuration.
Sir, nickel, sir, argon, PDA, 4H2.
Yes. Then palladium. Just think a while. Palladium enjoys the most unique anomaly in the entire periodic table. Of course, thorium also enjoys. Thorium doesn't have any electron in the f orbitals in the ground state. Thorium, that is the second element in the actinide series. Yes, Mr. T.
Yes, sir.
Palladium.
Sir, palladium ର krypton 4010.
अब 5s0 ବୋଲି କହୁନ 5s0 କୁହ
5s3.
5s0 4010 ନ କହିଲେ ବି କିଛି କ୍ଷତି ନାହିଁ ନ କହିଲେ ବି କିଛି ନାହିଁ so it's diamagnetic, it doesn't carry any unpaired electron, hence it is diamagnetic in the ground state. Always say if nothing is said, it is in ground state because every element can be excited. Energy can be supplied so that one electron from the highest energy level goes to the next the excited state, next higher energy level, and then it returns back. It emits the characteristic radiation, and it may fall in the visible if it is the energy is falling in the visible region. Otherwise, it can fall in the IR region. It can fall in the UV region. So it will. And then what about platinum that we already have done? Let me tell you on your behalf, 6s1, 5d, 9. Of course, 4f14 is there. And before that, there is xenon configuration, right? Ismail?
ଆଜ୍ଞା sir.
Platinum କହିଲନି ମୁଁ କହିଲି ତମେ କିଛି କହୁନ ଠିକ ଅଛି?
ଆଜ୍ଞା sir, 4f14, 5d9, 6s1.
Yes. Now I wonder, don't broaden your hat, your chest. I wonder to the extent to which you are familiar, you are confident in the periodic table, all the elements. I doubt you will find any. Of course, you will find in the whole of India country, but it will be very, very marginal. I congratulate you, but don't widen your chest. You have to show your interest continuously without any decrease in your spirit. Then only I am here. Tiger जिंदा है. Tiger जिंदा है. Tiger अभी जिंदा है. Tiger मरा नहीं. It looks like it is sleeping. You have conquered. You have killed tiger. No, tiger अभी जिंदा है actually. Okay. Now comes today's program. We'll go a little faster. Well, I will be again taking this to discuss. First one will be atomic size, then ionic size, and there are two, in fact, three. For metals, it was metallic radius. That is, in the metallic crystal, in the solid state, when they are at the closest approach, then the distance between the two adjacent nuclei, half of that in the solid state. That was called metallic radius, because there are methods in X-ray diffraction that is taught in the solid state chemistry, solid state physics, how to determine the internuclear distance. So half of that in the solid state will be was called metallic radius. They were only valid for metals, and for non-metals, it is the covalent radius. So that is in a covalent molecule, particularly single bond. It's not a double bond. O double bond O, but you have to look for O single bond O in hydrogen peroxide. We will look to bonding later. So half of the covalent bond distance, nucleus to nucleus, in a covalent bond. This is independent atom. I mean, not covalently bonded. Of course, there is metallic bonding. There is a bonding called metallic bond, but that is not as strong as covalent bond, as near as the proximity is not as much as in metallic bond. So covalent bond and half of this will be called the covalent radius. This is the metallic radius. And later on, when lot of proficiency was attained in computer skills and analysis, digitization, and other things. And also, many metals were involved in covalent bonding. Ironically, there are many compounds. There are very many species, maybe ionic species, maybe covalent species. But once there is a metal, even if it has a covalent bond, which is the shortest distance between two adjacent nucleus, that should be the true metallic radius. I mean, atomic radius, half of the covalent bond, single bond. So since metals were not found to have covalent bonding with itself, later on, some metallic clusters, these are called metallic clusters in the vapor state, N8, Fe5. So metallic clusters were prepared, so they could find that in the clusters, Fe8 or Fe10, 10 iron atoms are forming a cluster, and they found their internuclear distance is less than the metallic radius. So therefore, it was found that overlapping of orbitals takes place in between the adjacent atoms, the overlapping of orbitals that take place in covalent bonding. While in metallic bonding, you will know that all the valence shell orbitals, they will overlap with each other to form a gigantic molecular orbital with different energy levels. And the lowest one is the HOMO, the highest occupied molecular orbital. We'll talk about molecular orbital theory in our chemical bonding program. Don't uh, worry about it. Now, they computed for metals also, they computed covalent radius. The first choice was to find any experimental evidence that the metal is involved in covalent bonding with itself in metallic clusters. Gallium is an element which forms Ga2. Digallium, which is dimer in the liquid state and solid state. So they can found the gallium size. This is a covalent radius. So what I mean to say, in the last 20 years, all the metals, they have been corrected to their covalent radii. Radii. Radius plural is radii. So you should not be surprised if somebody says, what is the covalent radius of sodium? You'll be surprised, how come sodium is involved in a covalent bonding with itself, with itself. So there are two cases in metallic clusters and in some polymeric species dimer, trimer, tetramer, which has been formed, which are also same as metallic clusters. They also are polymeric, and also some computation has been done. Had sodium been involved supposing they know sodium doesn't involve in sodium chloride, interionic distance in ionic bond they found in interionic distance. So, and then chlorine atom, the covalent radius, don't confuse with sodium chloride as same as sodium atom and chlorine atom. Once sodium becomes sodium ion, it shrinks. The size of the ion is much less than the size of the atom, which is neutral atom. And similarly, chloride, once it takes electron, it swells, becomes hefty, bulky. So I am not going to the details of how the computation has been done, if at all. They do not have any experimental evidence. And in every case, they found that the covalent radius is slightly less than metallic radius. It was needed for comparison, how the atomic size, because the covalent radius is the best representation of the size, because you cannot have a geometrical box where you can find a compass or a what we call divider. What is that? Two pointed um, you know pins. तब कौन थी?
The divider.
Divider, so that you put one pin on the nucleus and put the other pin on the outermost electron, outermost orbital, and find the radius. It's not possible, even in any experimental method. The experimental method is to find the internuclear distance. That is possible. So the best choice, best representation of the size is from the covalent radius. Metallic radius was found to be slightly greater, although earlier it was taken as the atomic size, but now all of them were given their covalent radii. And the third one, which is now obsolete, if somebody will set question, it will be for sheer overwhelming you. So this is van der Waals radius. Van der Waals radius. This is in the solid state between two non-bonded. Supposing it, we were talking of say oxygen. So this is one oxygen, O, double bond, O, whatever, and this is another oxygen. Sorry, overlapping, because it's covalent bonds, means this is another oxygen. And in this solid state, whether it is in the room temperature, it is a gas or liquid, you have to freeze it to its freezing point, make a solid, and then take the this between two neighboring atoms, the internuclear distance between two neighboring atoms in the solid state, non-bonded atoms, two non-bonded atoms, neighboring atoms, neighboring non-bonded atoms, and one half of that, it was called the van der Waals radius. It was necessary before, in the early 20th century, they had no compound where the noble gases, particularly the noble gases, could form a covalent bond. They were saying stable octet, stable duplet, so they didn't make any effort to prepare compounds, because they remain in the monoatomic state. They are monoatomic molecules, stable molecules, but monoatomic. So unless they find some compound, they cannot get the covalent radius. And they were prepared, their covalent radii were determined. So because For every element can have covalent radius, excepting metals which are solids. They cannot have their covalent radius, their metallic radius. But all the non-metals which remain in a bonded states to form a molecule like Cl2, O2, H2, P4, all these molecular species, they can also have their covalent radius. Because if you take the distance between two non-bonded neighboring atoms in the solid state, don't take metals, only non-metals. They had both covalent and van der Waals. But van der Waals radii were required for mostly for the noble gases. But nowadays, van der Waals radius was really found to be much higher than the coarse metallic radius is for only metals. Nowadays, for all metals also, you will find a slightly greater Harikoni covalent radius. That means van der Waals radius is much greater than covalent radius because they do not, even if it is solid, even it is Cl2 or H2 or N2 or O2, they come close, but not as close as the real bonding that is covalent as well as metallic. Metallic bonding also they come very close, but not to the extent that the overlapping of orbitals happens in covalent bonding. You understand everything?
Yes, sir.
Yes,
So,
sir.
so earlier, before 2010 or maybe 2005, when we were teaching to students in plus two stage, we were saying in a period the size decreases and suddenly it increases in noble gas because noble gas doesn't have a covalent radius. So since it is all it was expressed by Van der Waals radius, which is always greater than its corresponding covalent radius, which is not determined. So it appears that the atomic size decreases across a period, and then in the when you come to the respective noble gas in the same period, at the end you find there is an increase. So that is because nowadays you will not find any periodic table containing the atomic size data. All are covalent radius, and there is a decrease. There is a decrease till end. Of course, there are some anomalies that we will discuss today. Now I am showing you uh, period wise. Let us study. So in a period, first the normal S and P blocks elements, they're normal elements or representative elements, and the variation in size or any periodic property is almost regular, almost barring a few anomalies which are very unique and very periodic, very periodic. It's not haphazard or erratic. That what you find in transition series, transition groups. Now, what you find the when I say atomic radius now will mean covalent radius. Remember, they are now used interchangeably. Anybody says atomic radius means he's talking about covalent radius, even if it is a metal. So in period wise, it decreases. I will tell you where is the anomaly comes. It decreases till end, till noble gas. And the reason we will find out due to, in earlier stage, they were not given to calculate how the effective nuclear charge increases. You know, already I have told you that the inner electrons act as screening electrons, shielding electrons to the valence shell, the outermost electron or the valence electrons, to reduce the force of attraction so that the size increases. Had there been no inner electron, just think for a moment, about sodium is 3s1, a 1s2, 2s2, 2p6 were not there. And the electron was the last electron which will determine the size and determine all periodic properties. The last electron, 3s1, is there and no other electrons in between. But there are 11 protons. So the attractive force would have been much greater because there is no intervening electrons to screen. So the inner electrons act as mechanical barriers, a screen to reduce the interaction between the nucleus and the outermost electron, the valence electron. So we'll talk about that later. Due to we'll write increase in A and C at Z star. Effective ANC means effective nuclear charge. Sodium, if you ask sodium to the 3s1 electron, the actual nuclear charge is 11, but it will ask, "Hey, Babu, what do you feel? Do you experience the feel for 11 protons? Or what do you think? How many protons attractive force you are really enjoying?" You say, "No, I don't realize that there are 11 protons. Am I sodium? Yes, you are sodium. Yes, you are sodium. But I am not experiencing the presence of 11 protons in the nucleus. Why? Because some of the protons capability is being destroyed by the screening electrons. So the protonic charge, protonic the nuclear charge, that means the number of protons, which is really experienced by the valence electron. Due to screening effect, of the inner electrons, some influence of Z. Z means actual nuclear charge is reduced. So the extent of influence nuclear charge reduced by the screening electrons is called the screening constant. Screening electrons or shielding electrons. Screening is same as shielding. Is determined from a constant called from screening constant sigma, which is calculated from the Slater's theory. Slater came after Schrodinger's. He modified the equation for polyelectron species containing multiple electrons having screening effect, taking screening constant into account. So the Z star, which is the effective nuclear charge, ENC, is equal to Z minus sigma. To what extent it is destroying the nuclear charge? If supposing for sodium it is say 5, for example, we'll calculate that. So when you ask 3s1 electron how much of protons you feel that nucleus is carrying for you, So it will say 11 minus 6. मैं केते कहथिली 6 ना केते कहथिली सोई पड़लनी कि are you fast asleep केते कहथिली
No, sir.
अरे सिग्माटा केते कहथिली मन करो मु कहथिली केते 5 ना 6 कोन कहथिली तमर भी विस्मरण घटिलानी विस्मय विस्मरण घटुची मुते 5 कहथिली सो 11 माइनस 5 सो सी कहबो जे 6 6टा प्रोटॉन किंतु एक्चुअली अछि 11टा प्रोटॉन सी कहबो मु 6टा प्रोटॉन ए बेले बेले सिग्माटा कैलकुलेशन रे डेसिमल पॉइंट थाए जहाँ भी अच्छी 5.6 थी जदि से 11 माइनस 5.6 सब 5.4 से कहे 5.4 प्रोटॉन रो मु इन्फ्लुएंस न्यूक्लियर आई मीन अट्रैक्टिव फोर्स मु एक्सपीरियंस करूची बाकी तबे कहूछ जदि 11टा थिबो थिबो बाट मारण हो गला तार इन्फ्लुएंस बिकॉज ऑफ द स्क्रीनिंग इलेक्ट्रॉन्स 5.6 or something is being removed or is being taken away snatched away so that the valence electron cannot feel that many protons influence that is determined from the screening constant. So in a group size increases, we must write down like this, increases, and एठी कौन लिखले हाँ yes in a period decreases and it increases due to not due to decrease in effective nuclear charge. It is due to increase in the n factor. That is radius of the valence shell. Of course, n is principal quantum number. Radius is some constant 0.529 z square by n. Actually, it is z star square now. In polyelectron species, whenever you write z, you must write z star. There is definitely screening effect, screening constant, and hence Z is not used, it's Z star which is used for any calculation. So since you will find that along a group, Z star, the effective nuclear charge remains constant, more or less constant. People
Sir,
think, yes,
sir, Z square by
n by n, I'm so sorry. I'm so sorry. So down group, people think that the effective nuclear charge decreases. That is why there is increase in size, decrease in ionization enthalpy. No, the effective nuclear charge you will calculate because it goes to higher and higher cells. Lithium was 2s1, sodium is 3s1. It goes farther away. Oh, no, this is wrong. Again wrong. N square by Z.
N square.
Ah. તમે correction कल but ठीक रे correction कलनी उल्टी मु it is directly proportional to the square of principal quantum number and inversely proportional to now it is Z star. Previously for hydrogen like species it is Z. It is 3 for Li2 plus 2 for He plus and 4 for plus Be3 plus. But now in multi-electron species you have to take Z star. Screening effect comes into force and for all periodic property which is determined from the valence electron, the nuclear charge is not the true nuclear charge but the effective nuclear charge. This many angstrom. So since Z star remains more or less constant, the n factor is important. More is the n, more is the radius. And also the force of attraction or the energy, which is force of attraction is K, Q, the ZE square. Z is here, Z star by R square. So this R is dependent on N factor. So ultimately, more the R, less is the force of attraction. More the R, more the N. More the principal quantum number of the valence electron. If it is sodium 3, if it is potassium 4, more is R. More is the R, less is the force of attraction. And less is the force of attraction, size is more. The ionization enthalpy is less. Right? Understood?
Yes, sir.
Yes, sir.
But you will find a very interesting thing. What we'll say, the middle row anomaly, which is very, very profound in the fourth period in the P block. This is due to the D block contraction, or this is also called Scandide contraction. Because the screening effect of different orbitals in belonging to a particular cell, S is greater than P is greater than D and greater than F. More the number of nodes, radial nodes, less is the screening constant. Supposing you have for S an S orbital having, I'm talking of not, you know, uh, mm, see, NS or NP, whatever, NS, NP, ND, NF, 4S, 4P, 4D, 4F. So penetration wise, S is more because 4S has 3 radial nodes. It has, uh, 3 small mountains before the big mountain. 4S has 3 nodes, so it has 1, 2, 3, and then the big one that goes to infinity, that is not considered as a node. So more the penetration, more is the screening effect, because those penetrating small mountains, they will screen more. So S orbital also screen maximum, then P, then D, and F. 4F has no radial node, so its screening effect is less. So the screening efficiency goes down from S to P to D. Same trend as penetration. That is why in the D has lower screening effect than P and S. And see, I will tell you, when you jump from zinc to cadmium in the fourth period, these elements, gallium, germanium, arsenic, selenium, bromine, krypton, which follow after 3D, because since 10 elements have been already covered and D has a poor screening effect than S and P, so there is a gradual, since more is the screening effect, less is the force of attraction. Less is the screening effect, more is the force of attraction. Right? So since D has a less screening effect, so there will be more attraction, there is a decrease in size. That size reduction is called the D block contraction. The D series, there is a size contraction. We shall see that. So it decreases the size to such an extent, the nuclear pool has increased to such an extent that when you come to gallium, you compare with the preceding element in the respective group, you'll find although a new cell has been added, this was 3p1, this is 3p, this is 4p1. Even then, the size of gallium is almost same as that of aluminum. Almost. Or the increase is Very minimal. Same is the case with germanium, arsenic, selenium, bromine, krypton. You will find their atomic sizes, the covalent radii, are slightly greater than their preceding elements. But you'll find the significant rise in the size will go from carbon to silicon, nitrogen to phosphorus, oxygen to sulfur, because the d block contraction has not come. The d block contraction starts from the post period. So gallium, the first brunt of the d block contraction is felt by gallium. So gallium size hubahu aluminium sangare saman. But ଏମାନଙ୍କର size ବହୁତ କମ ଅଧିକା, ବହୁତ କମ ଅଧିକା. And you will see, ଯେତିକି ଆୟନାଇଜେସନ ଏନ୍ଥାଲପି କମିବା କଥା ଡାଉନ୍ ଦି ଗ୍ରୁପ୍ ଆମେ ଦେଖିବା ଯେମିତି କମିବା କଥା ସେମିତି କମିବନି. The reduction ionization enthalpy to come, but ବହୁତ କମ. And even the gallium has little more ionization enthalpy. So far as size is concerned, it is more or less same. But as far as ionization enthalpy is concerned, that is not will be the same trend, because it is a real energy term. The amount of energy required to remove the outermost electron from the gaseous isolated atom. You have to make it a gas and you have to make it atoms. Break the bond if you have any dimer, trimer, anything. So then you see how much of energy you need to remove an electron, valence electron. So you'll find gallium has a little more, ionization enthalpy than aluminium. And all these from germanium to krypton, they will have slightly less, not much less. As you find there is a profound decrease in ionization enthalpy as you go from carbon to silicon, nitrogen to phosphorus. But that from phosphorus to arsenic, the decrease is very small. And then there is a decrease, no doubt. Once the D started, ta khata kholigola, so eti hele bi, so seteta tathapi the variation is not as profound as you find when there was no D from boron to aluminum in all periodic properties, whether it is ionization enthalpy or it is size or it is electronegativity. You will find the electronegativities will be more than what, down the group the electronegativity should decrease as the non-metallic character increases. So the decrease is not found. Here you find the aluminium also will have almost the same electronegativity, and here the decrease is very, very small. You will find. So all the periodic properties are unique, not according to the trend. Sometimes anomalies happen, particularly between aluminium and gallium. So that is called the middle row. This is the middle row anomaly. The middle row anomaly is suffered by these elements. Their all periodic properties are little, unique. Anomalous, most correctly anomalous. Right? So what we learned, that is group wise, there is another thing that we will study. That is from gallium to krypton. Krypton, yes. This is 31, this 36. These 6 elements, they get the brunt of the scandide contraction or the first D block contraction. I will show you all the data. Let me talk about the theory and then we will calculate how to find the effective nuclear charge by using this Slater's theory. And there is another which is called the F block contraction. And out of that, the most important is the lanthanide contraction and the actinide contraction, which is not, because most of the actinide elements are synthetic. After uranium, all are synthetic. Now you will find, since the F, you will find the notes in my file that I'll send you. They'll explain, because after hafnium, before hafnium, all these lanthanide elements from cerium to lutetium are there. So they have electrons in their 4f electrons. Since F has the poorest screening effect, 4f has no radial node, and therefore the nuclear pull is more. Lanthanide contraction will be more than 3D. I mean, D block contraction is less profound. F block contraction is more profound because F orbitals, they have the poorest screening effect. So the increase in nuclear pull and hence reduction in size is more pronounced. So much so that ଯେତେବେଳେ ତମେ hafnium କୁ ଆସିଯିବ, you will find their sizes are almost the same. Hafnium, zirconium size समान. जो increase है किसी नु. टैंटलम नायोबियम साइज समान सिल्वर साइज गोल्ड संगे समान मर्क्यूरी संगे कैडमियम समान थैलियम जो टिके इंक्रीज हम is very small, and all these they will suffer from little bit of, this is called the Ebb block contraction effect, because before thallium before hafnium the F series have completed, and that effect continues till mercury, and it also percolates to the p block up to lead. You will find all anomalies. You'll find thallium has the second highest ionization enthalpy. We'll talk about that. Boron, then thallium, because the F block contraction ର ଶିକାର ହେଉଛି, the victim of F block contraction, lanthanide contraction in the p block, ଏମାନେ ତ ପୁରାପୁରି ହଉଛନ୍ତି in the p block thallium, ତାପରେ ଏଫେକ୍ଟଟା ଧୀରେ ଧୀରେ କମି ଯାଉଛି, and so much so that its ionization enthalpy is greater than all these aluminum, gallium, indium, and only less than boron. Lead ଟିକେ କମି ଯାଉଛି. Lead has ionization enthalpy only greater than tin. ତାପରେ ଆଉ ରହୁନି. And we will talk about the details. We're now considering the covalent radii. You find that in a group it increases due to increase in n factor among the S block and P block. Only you will find the middle, due to middle row anomaly, gallium has nearly similar size. ଏଠି ଲେଖିବାକୁ ଭୁଲିଗଲି. Middle row anomaly, gallium has similar size as aluminium, and other elements like germanium, gallium, germanium, tabre yeah,
Arsenic,
Arsenic,
selenium.
arsenic,
selenium,
selenium. Then
bromine,
Bromine.
krypton.
ଏଇମାନଙ୍କର 1 2 3 4 5 ଏଇମାନଙ୍କର ତା ସାଙ୍ଗରେ ଗ୍ୟାଲିୟମକୁ ନେଇକିରି ଏମାନଙ୍କର their size is slightly greater, not much greater than their preceding elements in their respective groups. In their respective groups. Since ଆମେ ସାଇଜ କଥା ପଢୁଛେ, ସେ ମିଡଲ रो ଆନୋମାଲିଟା ଆମେ ସାଇଜ ବିଷୟରେ ଡିସ୍କସନ କରିବା. ଆମକୁ ସବୁ କହିଦେଇଛି. You will find middle row anomaly in ionization enthalpy, electron affinity, electronegativity ସବୁଥିରେ ପାଇବ. କିନ୍ତୁ ଆମେ ପଢୁଛେ slightly greater, କିନ୍ତୁ galliumର almost same. And F block contraction ରେ lanthanide contraction ରେ zirconium ର size it is felt in the D block 6th period ରେ ଆସିବ. Zirconium onwards, hafnium onwards actually ଲେଖିବାକୁ ପଡିବ. You will find zirconium is almost same as hafnium. Then niobium is almost same as what? Hafnium ପରେ କିଏ ଅଛି?
Tantalum.
And so on. Palladium is same as platinum. Silver is same as gold. Cadmium is same as mercury. एंड सेमानकर मध्य पी ब्लॉक रे मध्य इंक्रीज होउची टिके बहुत स्मॉल इंक्रीज होउची सो एमानकर बेसी ए जिनस तमे पाइबो साइज कथा तो हम पढुचे काई आयनाइजेशन एंथैल्पी कथा लिखिबा सो दिस इज ड्यू टू द एफ ब्लॉक कॉन्ट्रैक्शन और लैंथेनाइड कॉन्ट्रैक्शन एक्टिनाइड कॉन्ट्रैक्शन विषय कहीं ना ये हाफनियम रो साइज डिटरमिन हेइनी खाली कैलकुलेशन हेइची in quantum mechanical ये it's not been corroborated by experimental evidence x-ray diffraction rate कौनसी experimental method रे तार size determination हेइनी but the lanthanide series sorry actinides ମାନଙ୍କ भितर up to californium जाके सब हेइची and that decrease in size is due to actinide contraction actinide contraction effect आमे पाइने एबे कोन lanthanide contraction निजे lanthanide रहउची एवं तार इफेक्ट आमे पोस्ट ट्रांजिशन सॉरी पोस्ट lanthanide एलिमेंट्स दिस जो कहते याको कहते पोस्ट lanthanide एलिमेंट्स ऊपर प्रभाव पड़ुची एवं इवन पी ब्लॉक रे प्रभाव तार टिके पड़ुची अप टू लेट सो এটা আমি দেখিলে now it's time to show you the data analysis जोटा मु कॉटन कॉपी पेस्ट करके नहीं आसीबी एटॉमिक साइज ऑलरेडी हम डिस्कस कर सारे देख ये कोटा भल देखा एटा भल देखा जाउची ना एटा भल देखा एटा ठीक अछि देख इन ए ग्रुप हाइड्रोजन सबटु छोट देन 1.34 सोडियम होची इरो एंगस्ट्रॉम रे डेटा होची एंगस्ट्रॉम रे सोडियम 1.54 पोटासियम 1.96 रुबिडियम 2.11 मोटा हेगलानी सीजियम 2.25 फ्रांसियम 2.60 इन ए पीरियड धरम थर्ड पीरियड नेडी सोडियम 1.54 एंगस्ट्रॉम 1.35 1.18 1.11 1.06 1.02 0.99 0.97 आगुरु एगुडा हठात करी बढ़ी जाउथला धर फ्लोरीन 0.71 इटी थिला धर 0.9 कि 1.1 suddenly बढ़ीगला it is due to the data where van der Waals radius not covalent now सब कम पाइबो ता पूर्व एलिमेंट टू कम पाइबो however small it may be कम पाइबो किंतु because all are this covalent radii they are all covalent radii so you will find that the gallium and aluminum they have nearly but एठी नहीं it have better result aluminum is 1.21 gallium is 1.22 এটা latest এটা बहुत पुराना इतरे दिखाई चीजें there is increase but not much but this record is better so gallium 1.21 this is 1.22 very close and silicon 1.11 this is 1.20 the increase देखो carbon 0.76 carbon एठी अछि डेटा भिन्न भिन्न सोर्स रे डेटा सब समान मैच करबनी बट ट्रेंड विल मैच कार्बन 0.77 एंगस्ट्रॉम सडनली बढ़लानी सिलिकॉन 1.11 किंतु एठी 1.22 मात्र 0.11 बढ़ी एठी सेमती नाइट्रोजन 0.75 एठी 1.06 एठी 1.19 बट इन ए पीरियड कमी कमी जाउची ग्रुप रे फर्स्ट एलिमेंट नेक्स्ट एलिमेंट जो थे डी सीरीज आसीनी बहुत सिग्निफिकेंट चेंज होउची किंतु तापरे चेंज टा वेरी मिनिमल बिकॉज ऑफ द डी ब्लॉक कॉन्ट्रैक्शन और स्कैंडाइड कॉन्ट्रैक्शन गॉट इट सो एल्युमिनियम गैलियम रे डेटा देखियो एंड सी हाउ द साइज ऑफ this hafnium zirconium there are more or less same এটা পড়িছি স্ক্যান্ডিয়াম গ্রুপ রে স্ক্যান্ডিয়াম টু বড় ইট্রিয়াম ইট্রিয়াম টু বড় ইয়ে ল্যান্থানাম কারণ ল্যান্থানাম রে এফ ইলেক্ট্রন্স জয়েন হেইনি তা পূর্বরু কিন্তু হ্যাফনিয়াম হেলা বেলକୁ অলরেডি এফ ইলেক্ট্রন্স আসি গলানি 1.48 1.5 পাখাপাখি সমান 1.37 1.38 molybdenum 1.45 1.46 1.41 1.45 they are very close 1.26 1.28 but we might be thinking in a D series the size variation is very irregular we'll talk about that later not today I think today I will be telling you to calculate screening constant by Slater's theory 1.35 1.37 and silver is 1.44 gold is also 1.44 cadmium 1.51 mercury is 1.51 it data कौन कहूँ gold 1.45 silver 1 point, gold 1.36 kg. So methods are different. The determination, there are so many different methods to determine the covalent radius. So, but this is an old table. Anyway, so this is the theory that is required for the, and you find indium, this increase is small. The increase is small. Whatever increase was there from gallium to indium, from the 3D series to 4D series, after that is much. There is an increase in 0.2, but here the increase in 0.04. So because of the block contraction effect is also noticed here, the increase is small. There is increase, but small. But if you come to ionization enthalpy, you will find a big difference. Thallium will have so much high ionization energy that it will be coming second to boron. We'll be talking about that. Now, I have shown you the graph in a period wise helium. It is the hydrogen through helium कमिला एटी hydrogen टा एटी अछि एटी 1 this atomic number 1 8 पाखापाखि कोटा आसीबो एटी कमिला hydrogen to helium 8 रहबा कथा not in the axis कमिला then suddenly in third period second period को आसीगले lithium when a new cell has started. So when you come to the beginning of a period, you will find a profound increase in size with respect to its previous noble gas. Noble gas रे सही cell complete है गला सही subcell I'm sorry 2p6 complete है गला neon रे यार तो helium रे तो किसी नहीं 1s2 1 रे किसी p नहीं then 2 को पले आसला the radius in n square square रे change होची radius टा n square by z so पले गला बहुत दूर को so size टा बहुत बढ़ी गला then in a period it goes on decreasing not so drastically this decreasing till the series or the period completes with its corresponding noble gas neon ru sodium halide gote nuwa cell asigala 3 so suddenly increase kariya then decreases then potassium 4 then potassium calcium pore sarigala 10 टा element 10 टा d block element d series elements asigala from scandium to zinc 10 टा d series element 3d series asigala so the variation is not much but there is a scandite contraction but very anomalous so decrease is not as profound but decrease and then p block asigala the decrease is profound eta from gallium to krypton asigala then suddenly rubidium 5 then asigala yttrium to cadmium 4d series then 5p from indium to xenon xenon is 54 sarigala pun is 55 6s asigala then you enter into this is 4f there's some anomaly in the 4f then 4f sarla pore 4f then 5d series sarla pore puni 80 asigala kon 6p radon tapare 7 diya yani francium data nahi so in this way it varies and transition series ray it is less pronounced but there is a decrease small net decrease in size here is a fallacy we say there is a d block contraction but the real contraction is very minimal its effect is noticed this is a weapon to explain but in the d series if you compare between the first element scandium last element zinc you will find the decrease there is a decrease but not much कौन होची ता भितरे कमुची स्कैंडियम रु कमी कमी के किछि एलिमेंट पर्यंत कमुची पुनी सेम रहउची मोरलेस सेम रहउची लास्ट दीटा एलिमेंट को टिके पुनी बढ़ुची so that the first and last को compare करी गले the decrease is minimal now I leave it here we will discuss more about the transition series and group wise already हमें देखिलेनी group wise देखी साइलेंट ट्रांजिशन ग्रुप रे ड्यू टू लैंथानाइड कंट्राक्शन जिरकोनियम संगे हैफनियम रो पाखापाखि समान नाइबियम संगे टैंटालम समान एंड सो ऑन किंतु सीरीज वाइज जो चेंजटा होची प्रथम टिके कमुची पुनी कांस्टेंट रहउची पुनी टिके बढ़ुची ए विषय तार रीजन विषय डिस्कशन करबा क्वालिटेटिवली एंड बट गोटे इलेक्ट्रॉन न्यूक्लियस रे बढ़ला बेलको सॉरी गोटे प्रोटॉन न्यूक्लियस रे बढ़ला बेलको गोटे इलेक्ट्रॉन बढ़ुची कोठी बढ़ुची ना 3d रे 4s रिमेनिंग कांस्टेंट So screening electron boduchi. 3D is a screening electron. So in general purpose, because D has a different screening constant than S and P, we'll find. Sethipai there is a variation, but semti dekhiବାକୁ ଗଲେ ଗୋଟେ proton ବଢୁଛି ଗୋଟେ inner electron ବଢୁଛି, so they cancel each other's effect. So the size will remain same, but there is the change in size, but gradual change. There are 10 elements, gradual decrease and then remaining constant. When there is initial elements, there is screening effect is profound, so that the size screening increases. So the nuclear pool what happens, the screening increases. No, the nuclear pool is dominating. The number of electrons is not sufficient to screen and to reduce the force of attraction, so that there is a net effective nuclear charge increases. So there is a slight decrease in size. More number of electrons, they will definitely make the whatever screening happens, this being nullified, balanced by the increase in the nuclear charge. So the size remains same. That means effective nuclear charge remains more or less constant. Towards the end, when this cell is subcell, the D subcell is complete. Copper is 3d10, zinc is also 3d10. So it attains a spherical symmetry. All the d orbitals, all the lobes are having electron density. So it looks like from a distance it is a sphere. The assembly of all the d orbitals. So once it looks like a sphere, it looks like a s orbital, spherical symmetry ଆସିଗଲା ତାର, like spherical symmetry. So ପୁଣି screening effect ବଢିଗଲା. S has more. So ଯଦିଓ ଏଇଟା S ନୁହଁ କିନ୍ତୁ spherical symmetry ବଢିଗଲା ମାନେ force of attraction କମିଗଲା, size copper zinc ଟିକେ ବଢିଗଲା. But nuclear charge ବଢୁଛି ନା, so ultimate, if you compare between first and last, there is a decrease. So this is the physical interpretation that we make, give the explanation how there is a change in size. Towards the end, there is again increase. So you'll find scandium is 1.44, Camilla 1.36, 1.25, 1. तापर बोरस समान रहिला 1.25, 1.2. Towards the end, 1.28 copper, 1.34. So same will be the trend here. Same will be the trend here in the 4D and 5D series. So I have already told you, just write down the notes. And now, କେତେବେଳେ ଦେବ ତୁମର କ୍ଲାସ୍ ସ୍କୁଲ ଅଛି?
6:50
ଛଅଟା
6:50
ତ ମୋତେ ଖାଇବ ନା? I think we will ଏଟା ପଢ଼ିଦେଇଛି, ନିଡଲରେ ଆଲମାରି ପଢ଼ିଯାଇଛି. ଏଇ ଯେଉଁ କ୍ୟାଲକୁଲେସନ୍ ରିଲେଟିଭିଷ୍ଟିକ୍ କଣ୍ଟ୍ରାକ୍ସନ୍ ଏଫେକ୍ଟ ମୁଁ ପରେ କହିବି. ସୋ ଏଇ ଯେଉଁ କ୍ୟାଲକୁଲେସନ୍ଟା ଏଇଥିରେ ଅଛି ନା କେଉଁଥିରେ ଅଛି? ଏଇଥିରେ ରହିବା କଥା, ଏଇଥିରେ ନାହିଁ, ଆଉ ଗୋଟେ ଫାଇଲ୍ରେ ଅଛି. So we'll talk about that ଡେରି ହେଇଯିବ next time, because say screening constant and finding out Z star, you will be required to explain all other periodic properties. So that is important. So ame au lobo na kari kids already 6:38. Seta saribani 15 minute bhitere we close. Ame Wednesday dino ame seta sardaba. Seta prathame sariba Slater's theory to calculate sigma and then Z star. And देखिवा पुणी आउथरे देखिवा काहेकि in a period Z star increases. जदियो स्क्रीनिंग इलेक्ट्रॉन बढ़ुची किंतु देखिवा कैलकुलेशन तो देखिवा जे स्क्रीनिंग कांस्टेंट डेसिमल रे बढ़ला बेलकु 0.35 लेखा बढ़ला बेलकु इयाडे गोटे लेखा न्यूक्लियर चार्ज बढ़ुची 1 लेखा. तेणु Z minus sigma, that is Z star, is increasing across a period. You'll find एटा 3.35 बढ़ला बेलकु एटा बढ़ुची 1 लेखा. But down the group, देखिवा Z star will remain constant. But since n increases, so the radius increases, n square by z, and also the force of attraction decreases, current z square by r. I mean, zd square by r square. R square ta tole achi. Force of attraction decreases, size increases. So, bye bye.
सर
हम्म हम्म
सर सर ଏନସିଆରଟିରେ ନୋବେଲ ଗ୍ୟାସକୁ
हम्म
ସାଇଜରେ ବଡ ଲେଖା ହେଇଛି।
हम्म
ଏନସିଆରଟିରେ ନୋବେଲ ଗ୍ୟାସ ଏନସିଆରଟିରେ ନୋବେଲ ଗ୍ୟାସର ସାଇଜ ବଡ ଲେଖା ହେଇଛି। କିନ୍ତୁ
ସେ ସବୁ
ଏକ୍ସାମରେ ଆମେ
ଏନସିଆରଟି ବୁକ୍ କଣ ଲେଟେଷ୍ଟ ଏଡିସନ ରେ ବି ସେଇଆ ତମେ କୋଉ ଏଡିସନ ଆଣିଛ ଲେଟେଷ୍ଟ
ଆର ବର୍ଷ ହେଲେ
ଆର ବର୍ଷ ମାନେ ଲେଟେଷ୍ଟ ଏଡିସନ ସେ ନୁହଁ କାମ ସେ ନୁହଁ କାମ ଆଉ ଯଦି ତମେ ଯଦି ସିବିଏସ୍ଇ ପିଲା ତମେ ତ ସିବିଏସ୍ଇ ପିଲା କି କିଏ ନୁହଁ ତ
yes,
କିଏ ତମେ
ଆମେ
ସିବିଏସ୍ଇ
ସିବିଏସ୍କୁ ଆସିଲୁ
ତମେ ସିବିଏସ୍ଇ
ଆସିଲୁ ଆଜ୍ଞା
ଆଁ ଓଡ଼ିଆ ଓଡ଼ିଆ କଣ ମ ସିଏଚଏସ୍ଇ ନା ସିବିଏସ୍ଇ ତମେ
ସେ ସିବିଏସ୍କୁ ଆସିଲୁ
ସିବିଏସ୍ଇ ରୁ ଆସିଲ
ଆଜ୍ଞା ସିବିଏସ୍ଇ କୁ ଆସିଲୁ।
ହଁ ଆରେ ମୁଁ ଗୋଟେ ଇଣ୍ଟରେଷ୍ଟିଂ ଜିନିଷ ମୁଁ ଦେଖୁଛି ଆଗରୁ ଓଡ଼ିଆ ପିଲାମାନେ ସିବିଏସ୍ଇ କୁ ଆସିପାରୁନଥିଲେ ଏବେ ଯାହା ହଉ ଆସିଲେ ଭଲ ହେଲା ସୋ ତମେ ସିବିଏସ୍ଇ ଯଦି ବୋର୍ଡ ଏକ୍ଜାମିନେସନରେ ତମେ ଯଦି ପଢିବ ତାହେଲେ ତମେ ସେ ଏନସିଆରଟି ବହିକୁ ଫଲୋ କରିବାକୁ ପଡିବ ସେଟା କାହିଁକି ବଢିଗଲା ବୋଲି ଯଦି କିଏ ପଚାରିବ ତମେ କହିବ ଇଟ୍ ଇଜ ଭ୍ୟାନ୍ ରେଡିୟସ୍ ସେଥିପାଇଁ ବଢିଗଲା ଏଇଟା କୋଭାଲେଣ୍ଟ ରେଡିୟସ୍ ଏଇଟା ଭ୍ୟାନ୍ ରେଡିୟସ୍ ସେଥିପାଇଁ ବଢିଲା ହେଲା ସୋ ଆଇ ରିଏଲି ୱଣ୍ଡର ମୋର ମୁଁ ସବୁବେଳେ ରେଫର କରେ ଏନସିଆରଟି ବୁକ୍ କୁ କାହିଁକି ମନେ ପଡୁନି ଏନସିଆରଟି ବୁକ୍ରେ ନୋବେଲ ଗ୍ୟାସ୍ ଗୁଡାକର ବଡ ଦେଇଛି ଆଠୁ ଦି କରେସ୍ପଣ୍ଡିଂ ପ୍ରିଭିୟସ୍ ଏଲିମେଣ୍ଟ ଇନ୍ ଦ ରେସ୍ପେକ୍ଟିଭ ପିରିୟଡ଼ ଅଧିକା ଦେଇଛି ତମ ପାଖରେ ଏ ବହି ଅଛି ଏନସିଆରଟି ବହି ରଖିଛ ସ୍ୱୟଂ
ଆଜ୍ଞା ସାର୍
ଏନସିଆରଟି ବହି ସବୁ
ଆଜ୍ଞା
ରଖିବାକୁ
ସାର୍
ପଡେ
ସେଇଆ ଦେଇଛି।
ଓକେ ସେ ତାହେଲେ ତମ ପାଇଁ କିଛି ନାହିଁ ତମେ ତ ସିଏଚଏସ୍ସି ବାଲା ତା ପାଇଁ ଟିକେ ତାଙ୍କ ବହିରେ ଏନସିଆରଟି ବହିରେ ଯାହା ଲେଖା ହେଇଛି ସେଇ ଅନୁସାରେ ତାଙ୍କୁ ବୋର୍ଡ ପରୀକ୍ଷାରେ ବଟ୍ ଏଇଟା କେବେ ଇଏ ପରୀକ୍ଷାରେ ପଡିବନି ଅବଶ୍ୟ ନିଟ୍ ପର୍ଟିକୁଲାରଲି ନିଟ୍ ଏକ୍ଜାମିନେସନ ବେଳେବେଳେ ପଢୁଛି ମାନେ ପୁରା ଏନସିଆରଟି ବହିରୁ ଟିକେ ଆନାଲିଟିକାଲ ପଢୁଛି କିନ୍ତୁ ଏନସିଆରଟି ବହିଟା ମୋଷ୍ଟ ଇମ୍ପୋର୍ଟାଣ୍ଟ ଫର୍ ନିଟ୍ ମୋଷ୍ଟ ଇମ୍ପୋର୍ଟାଣ୍ଟ ସେଥିପାଇଁ ମୂଳରୁ କହିଦେଉଛି ଲାଇନ୍ ବାଇ ଲାଇନ୍ ଏନସିଆରଟି ବହିଟାକୁ କର ତୁମକୁ ଯୋଉଟା ଠିକ୍ ଲାଗୁନି କିନ୍ତୁ ତାକୁ କର ଆଣ୍ଡ ଟେଲ୍ ମି ଯେମିତି ମୋତେ ବିସ୍ମୟ କହିଲା ଯେ ଏଇଠି ଆମେ ଏହା ପାଉଛୁ ସେଇଟା ମୋତେ କହିଦିଅ ମୁଁ କହିଦେବି ଯେ ନାଇଁ ଏଇଟା ଭୁଲ ଭୁଲ କିନ୍ତୁ କାହିଁକି ଠିକ୍ ନା ସେଇଟା ଭ୍ୟାଣ୍ଡୁଭଲ୍ସ ରେଡିୟସ୍ ଦେଇଛି ସେଟା ଜାଣି ରଖିଥାଅ ବାଏ ବାଏ
ଥ୍ୟାଙ୍କ ୟୁ ସାର୍।
ଥ୍ୟାଙ୍କ ୟୁ ସାର୍।